And kind of the fact that we're kind of in where physics was maybe in the early Middle Ages. Everybody comes up with their idea. There's no unified theory. People are a little bit argumentative about things because there's no way to really resolve. Some people quote Volvo. Some people quote Pascal. It's kind of a Wild West, and a lot of the time Partha and I spent trying to understand what's going on and is there a solution, but mainly we used to kvetch about it. One term that we used to make fun of a lot is the term of biological plausibility. And, you know, it's a term that you can do a lot of things with. So I will try to pretend I am working within a biologically plausible framework that's somewhat different from what Tommy was talking about. And again, since the science of biological experiment is still so primitive, we can't resolve these things yet. So it gives a lot of freedom, but it also gives a lot of room to kvetch, and I really miss Partha for that. We had great conversation. We didn't just kvetch about neuroscience, we kvetched about economics, politics, and everything. But I really miss those conversations. They were great, great conversations. So here are the 26 script LaTeX characters. If you've written papers, you've used some of them. And here is a particular one that I hope you will try to detect in the coming images. So what you're supposed to do, try to do this, either you can do it or you can't, is fixate at the cross in the middle. Okay, don't try to move your eyes around and try to decide if the epsilon, the script E, appeared or not. And here it's now going to happen at some rate. So the idea of this experiment, it's not a well controlled here in the room, is to emphasize a few things. Let me go to the top of the talk. One of them is that we can detect the presence of an image. Make it bigger. This thing. We can detect the presence of an image even if we're not looking at it. Even if we're fixating at the center of the scene, we know that a certain object appeared, and that was that epsilon. Okay? Okay, so that's called detection without saccade or changing the direction of attention even, because very quickly, pretty reliably, you know if the object was there or not, but you did not move your eyes or move your attention because you didn't know where to move it to. Another thing that's clear from that experiment is that there's a problem with distractors. Okay, that's a real problem. That's called the curse of clutter in vision. And if the distractors are very different from the object you're trying to detect, such as the K from the epsilon, if you remember the sequence of images were only Ks, it was really easy. The S's and the epsilons were a little harder, and when there's a mess of all kinds of characters, it's probably harder. So there are degrees of difficulty, but the system can do it. Something's going on. There is a translation invariant operation going on, and Tommy, I'll skip this because Tommy really presented a lot about the ventral stream that I will skip that. So I call that detection. We have an object we're trying to detect. We can do it even if we're not moving around with our eyes or with our attention. There's the possibility of doing that. And that immediately tells us it's some built-in translation invariance in the system. And how do we get that? Now on a computer with random access memory and very fast computers, you can do what the people who work on the Pascal project do, and that is you scan the whole image. Okay, and you can access the data at any point sequentially, or if you have 10 processors, you divide the image up to 10 processors, and they do it, and each of the processors has Pedro's best program and detects whether there's a face there. And if you have 100 processors, you'll do it even faster. But the brain doesn't have that. So that's a really interesting problem. Now, there's a kind of dual problem, which is if you're fixating at that cross, and I tell you to pay attention to the upper right-hand field, but don't move your eyes, just attend to it, you can tell me what objects I put in the upper right-hand. Okay? So that's another phenomenon of translation invariance. You're not moving your eyes to that place, but somehow you're classifying the objects that's there. So that means that somehow you're able, assuming that we just have one classifier that classifies objects somewhere in IT, like Tommy was explaining, or maybe a combination of IT and prefrontal cortex, then that information is being moved from that extrafoveal location to the central module that is going to classify. So those are questions, just translation, invariance. Of course, there's rotation and other things that puzzle me, and I'm interested in thinking about them. So I want to talk a few challenges. Learning, recognition, and invariance with what I call network constraints. So I could have written biological plausibility, but I'm a little bit afraid to use that term. So here are the rules of my game. The brain cannot compute complicated matrix multiplications. It can't divide quantities. So I'm really going to tie my both hands behind my back in order to try to solve this problem. So neurons are binary, and they're all really perceptrons. All they can do is add up their input and compare it to a threshold. And then they're either 1 if they're above threshold or 0 if they're below threshold. Synapses, the thing that connect the neurons, have to be positive. They can't be negative. There's no such thing as and I will come to it. There is inhibition in the brain. There's no such thing as a negative synapse. You need to use inhibitory neurons in order to get. So synapses are positive. They're discrete, and they have only a small number of states. So we're going to be playing between 2 states and 3 states. And actually, one of the things, if I get to it, till when do I have? Because we're running late. So when should I stop? Say that? Okay. So I will show you that you can get a big boost by going from 2 states to 3 states. But if you look at the literature on synaptic potentiation and depression, of course, everything in biology is not exactly discrete. There's variation, there's noise, but synapses typically, in experiments, have 3 states, 2 or 3 states. Learning has to be local. You can only update a synapse based on what's going on in the 2 neurons that it connects. It can't know anything else from other synapses. And you basically have a prefixed threshold. Maybe it's not the same threshold in every unit in your network, but every module in your network, there's some uniform threshold that's predetermined, and that's what you play. Okay, you can't start changing thresholds of different units all the time. So here's a picture of my problem. I tell you to attend here. Okay? No, you're fixating here, but I tell you to attend to this region. Somehow you can get the information here to a central classifier that is able to tell you it's a T. Okay? So I want to understand how the connections between the input to the classifier are updated in order to obtain classification, and I want to think of how the data is translated. Oh, I'll get to that. Okay, sure. Because I want to produce a classifier within the rules of my game. So this classifier, what I wanted to do, it's going to have inputs that are features associated to a location, just like Pedro used hog features. Tommy was talking about Gabor filters, or his random features, but they're local, so they have a certain location associated to them. So that would be your input. And the classifier is an abstract module of neurons where there's a population coding for each class. And the reason you want a population coding for each class is that, in the brain, the only way to get a stable response is from the activity of a self-sustaining group of neurons. You can't have one neuron telling you that it saw your grandmother, the grandmother's cells, because it's unstable. There's so much noise, and so you can't rely on one neuron. So you do really want to represent it as a population, and we'll see that there's a lot of, that we gain a lot from doing that in a minute. So there's going to be populations, and it's going to be supervised. So when I'm learning, I'm showing an example of a letter T, and I'm lighting up the population of neurons in the A module that correspond to the T, and I perform Hebbian updating of the synapses. I probably won't have time to talk about the feedback from A to W, but that's a very interesting question too. By the way, in the brain, there's so many feedback connections going backwards in that hierarchy that Poggio told us about, and we don't really understand what they're doing. I will mention a few words on that later. So, how do we learn? So, the most basic, bare bones Hebbian learning says this. You take two neurons, when they're black, they're on, okay? So this one is on, and the upper one is on. The upper one represents one neuron in the population coding for a particular class, and it's on. If these two are on, there's some probability that the synapse moves from state 0 to state 1. Let's say they're just two states. It's already on. It'll stay on. But if it's off and the two neurons are on, there's some probability, which I call long-term potentiation probability, that the synapse turns on. And if the presynaptic neuron is on and the post one is off, there's some probability that the synapse will turn off if it's already on. Okay? Now, this is a very simple local rule. It only depends on the two neurons. And it has a lot of problems if you're trying to classify. One of which is that if you have an object that has lots of on features, say you take a written zero versus a 1. The 0 has many more features in your pool of features. Whatever features you use, it's got more stuff than the 1. And so you'll get more things potentiated for the 0. And then if you're using a common threshold for the units that represent 0 and the unit that represent the 1, you're going to have a problem. Everything's going to be flooded for the 1. For the 0 if you have a threshold that will turn on some of the 1. So it's very hard to calibrate. Now, there are ways to do this in machine learning and in other types of computing. You can normalize synaptic weights, you can all kinds of things. But we still want to play with a rule that we're doing local learning. And so the way that, the simplest way to do this is to say, yes, you're doing local learning, but you can only update the synapse, you can only potentiate it if the total field that the synapse is feeling is below a certain level. So let's say it's below threshold. Okay, that's what we call field-dependent learning. So if the two neurons are on and the synapse is not potentiated, and the field is not too large, you can potentiate. But here you see there's already 4 potentiated synapses, and this pattern is presented. The field on this neuron is already high enough, and so this the update. Okay? Does this remind anybody of any learning algorithm that they're familiar with? Well, this is basically a very discrete version of the perceptron learning rule. Okay? If you think about it, what does the perceptron learning rule do? If you make a mistake, you make a change. If you don't make a mistake, you stay. So that's exactly it. If the field is above threshold, okay, you don't update because it's okay. If it's below threshold, you allow the synapse to update. And the same thing for depression. You can do the same thing for depression. If the field is below threshold, you don't depress. If it's above threshold, you allow it to depress. If the presynaptic neuron is on and the post is off. So this is a perceptron learning rule, but with a very constrained type of perceptron that namely the weights are positive, The threshold is fixed, and so you don't have all the power that a perceptron could give you here. So here's just an illustration of this fact. If you take, say, all the handwritten zeros and ones, say, in the NIST data set, and you choose some features. So think here, oriented edges, binary oriented edges, and you look at the probability of the features on the object versus the probabilities off the object. You see these very different distributions from, this is 8 and 1. The 1 has a lot of features that are high probability on the 1, very low probability on the rest. The 8 has a lot of features that are kind of intermediate. And so if you don't use the field-dependent learning rule, you can't get these perceptrons to work. Now, of course, if you use the perceptron learning rule, it's a different matter. The actual perceptrons, I'll come to that. But the field-dependent learning rules allow you to regulate the fields that each neuron sees and allows you to obtain reasonable classifiers. And I'll get to that in a minute. But the point here is to see that the average number of synapses that get potentiated to these different classes is more or less the same, and this is only thanks to the to this field-dependent local Hebbian learning rule. Now, one other thing is potentiation and depression are not guaranteed; they're stochastic, and that means that every time you train this on the same set, you're going to get a different classifier. So it's a randomized classifier. And that's why the fact that you have a population of 100 neurons in the abstract layer coding for a particular class, each one of them is producing a different classifier due to the randomization. Okay, we'll get to that in a minute. These are the probability of occurrence of a certain feature. Each point is a feature at a particular location. This is the probability it occurs on the object. This is the probability it occurs on all the rest. Think of classifying one against all. If you think about Rob's talk yesterday about one way people do multi-class, one against all, and then you have a bunch of one against all classifiers. So you use a binary classifier, but in many. So one way to get a big improvement is to say we want, see what this does, the previous method with binary synapses only latches on to features that are high probability on the class and low probability on the rest. But I'm beginning to feel that the most important features in classifying shape are actually features that don't occur on your class, but might occur on others if you're doing classification. They're very, very important, these features. Okay? If you see something in the middle of the image, you know it can't be a 0, because the 0 isn't in the middle of the image, things like that. And so how do you introduce that within the rules of the game we're talking about? What you do is you introduce 3 states to the synapse, and you introduce a global feed-forward inhibition. Okay? The inhibition doesn't depend on learning. It doesn't depend on it's a hardwired thing that basically says, I add up the activity in the input layer and I subtract the total sum of the activity from what the neuron is computing, from this weighted sum of the synapses and the features. And this allows you basically, you can see it algebraically, to get a negative weight, a 0 weight, and a positive weight. Okay? So now, if you have this and it's kind of at the 0, at the 1 state, this is kind of the intermediate state, and you have the presynaptic neuron on and the post off, you can get it virtually, it gets depressed to the 0 state, and then when you compute it with the inhibition, it basically gets a negative weight. Okay? But the inhibition is not something that's learned, it's not something that's updated, it's a hardwired thing. So with a little bit of inhibition, and inhibition is prevalent in the brain, it's something that serves many purposes, stabilizing systems and so on and so forth, and here it happens to serve the purpose of allowing me to introduce what I call negative features. And if you take 1 perceptron per class, so 10 perceptrons, using this very constrained learning, when you go from 2 states to 3 states on this MNIST, you have a great improvement. Still lousy, weak in Rob's terminology. It's a weak classifier, but it's a huge improvement from 2 states and 3 states because of the importance of singling out. And somehow in the neuroscience literature that talks about discrete synapses, I don't think this aspect of having the 3 states this way is sufficiently appreciated. Now, you use 1 perceptron per class, so that's 10 perceptrons, and you basically see which one fires. If 2 of them fire, you can't decide. Now, let me just say that if you train a linear SVM on these features, which is, again, 1 against all SVM, not each pair of classes, but again, 10 SVMs, 1 against all, with these features, you can get very nice results, okay? So features do matter. I mean, you don't get this with other features. These are just oriented edge features that are invariant to illumination. Okay. But, as I said, for other reasons, we wanted to have multiple perceptrons coding for each class. Not necessarily for the purpose of high classification rate, but for the purpose of how do you represent this in the brain. Ultimately, we'll represent it because the units in this level are, in each class, are connected with potentiated synapses. And there's a whole theory of recurrent networks that tells us that you can, if you have subsets of neurons that are whose units have synapses that are potentiated, if you start just a small subset, because of the dynamics of the network, you will get that the whole subset starts acting and starts being activated, and the activation is stable and sustained. Okay? So that's a way to represent the classification, but it turns out because the learning was random, each one of these guys for each of the classes is producing a different perceptron. So in memory of the randomized forest thing, here you have randomized perceptrons, and that makes a huge difference. So with 2 states, you can get a 92% classification. With 3 states, it's getting close to what the SVM is doing. But again, the states they're just 3 states, and the neurons are all with a fixed threshold, and there's nothing else you can change in this system. So this is a system that has very, very strong constraints, and because of, in fact, sometimes due to these constraints, we are able to gain some interesting improvement in classification, such as the randomization, and the use of inhibition here is very important to get access to negative features. And so now I want to say a few words on the invariance. So in general, and this is something that Tommy talked about and Pedro talked about, there are 2 ways to handle invariance. They're not exactly disjoint from each other. Either you mod out the variable you're interested in at the local level in terms of local features, okay, through maxing, say. So for example, oriented edges are modding out variability in photometry. That's why we use oriented edges. Almost every application in computer vision uses some version of that, okay? Complex cells mod out local translation invariance, okay? They don't mod out global, they mod out local. Or, if you go back to Amit's talk yesterday, if you have a global object, you can try to mod out in the classifier. Namely, you actually explicitly loop over the transformations on the data and see which one performs optimally in a distance or in some classifier or something. Now, these are not exactly disjoint things, and what are the level of local is hard to define. And indeed, I totally agree with Tommy. There needs to develop a theory about, what's the best way to deal with this trade-off. Obviously, if you mod things out locally, due to Taylor's formula, you have a much more restricted set of transformation to mod out. And if it's local enough, it'll only be translation, maybe rotation. And if it's a little bigger, it's got to be more. And so, these are hard questions. Now, just translation. In this problem that we were talking about of translation invariant classification, we know that to classify this T, we need to preserve some spatial information on the location of the features. You can't just jumble them into a bag and get reasonable classification. So we need to transfer the information in this upper left-hand corner to the classifier with preserving the relative locations of the features. Now, again, on a computer, you just do it. You just move the memory from one place to the other. In a wired system where each one of these units is just a perceptron, and it just sums its local field, well, you could connect this unit. Here, there's only two features, little x and big X. You can connect this unit here to all the little x's in the whole image. Okay? If you knew that the t is only going to fall on disjoint patches of the reference grid, then that would be no problem. Unless there were shift of the reference grid. Now, this could be a small reference grid, and this could be on a course. You don't have to think of this at the resolution, say, of V1. This could be happening in V4, which is a much coarser resolution. You need to take every shift of the data in the image and replicate it. So you make a stack of replicates, okay? And so this stack here, basically, instead of one image now, has as many copies of the size of the reference grid as there are pixels in the image, or as there are translations you're interested in. And if you were doing rotations, there would be multiply that. Okay? That's what I call the replica model. Once you have that, and you select a certain location, that's where I told you to attend, the input to the classifier can just do a simple summation, and only the locations that are only the location that's selected contributes to the input to the classifier. Okay? So there, as opposed to the original setting where this connected directly to this, and then everything gets lumped together, spatial information gets lost, clutter from other sub-images gets confused with the data you're interested in, this allows you to select a location and with simple computations of adding up inputs and thresholding them, get the input to the classifier. Is this biologically plausible? I don't know, but what you can show is that this seemingly artificial replication of translations of the reference grid can be recast as replications of this input feature layer as many times as there are coordinates in the reference grid, which isn't so big. The reference grid is not a big reference grid. The reference grid on which we recognize is known to be not that many pixels. So let's say 1,000 replicates of your features. And if you look at, starting from Hubel and Wiesel's work and on, when they stick electrodes orthogonally into cortex in certain layers, in V1 or V2, the neurons in the same orthogonal direction are responding to the same feature at the same location. So there are many replicates of feature responses in the brain, and maybe that's one of the uses. I just want to say that this same architecture, just flipping it, the dual, allows you to say, I want to now detect a face. That was the first thing I asked you to do in the experiment. I light up the model of a face in the W layer. So I light up high probability features in the face in the W layer, or maybe, if I'm more sophisticated, high probability and either low probability that needs to be inhibited. And then I spread this information to every one of the replicates of the reference grid. And that gets compared to the input. And finally read out in a layer that codes for location. There's well-known layers in the brain that can do it, that have direct connections from the feature layers. Okay? So again, this can be done by replicating the feature layer as many times as there are elements in the reference grid. But the catch is that the connections you need are very specific. Okay? This is not some randomly connected architecture. There's a very specific connection between a particular replicate of a particular feature at a particular location at this grid to, say, the W layer. How these things get added up and so on. But you can write this explicitly. And this is a way to obtain this dual translation invariance. And let me just say one more thing before closing. So this is how these things would be organized in using replicates of the feature layer. One thing, people have noticed is that the size of the, in IT, for example, in the early parts of IT, there are huge receptive fields responding supposedly to a rather, not a simple, but not such a complicated feature. And so, but then people noticed that when you asked the monkey or whoever to attend to something, these receptive fields seem to shrink. Okay? Now, it's not like the synapses disappear or the connections disappear. What this is, the way you can explain this in terms of this model is the following. When there is no attention, basically these units are doing what I said at the beginning. They're adding everything up. Through the replica layers, doesn't matter, but they're adding everything up. So they're seeing the presence of any feature, the feature that they like anywhere in the image, or anywhere in a huge subset of the image. It's only when attention selects either a particular location or a particular type of object you're looking for, is there a filtering, and then it seems as if these neurons are no longer responsive to such a large receptive field, they're actually responsive to a smaller one. Nothing has changed in terms of their connections. Nothing has changed in terms of the input. It's just that there's this additional aspect of selective attention that has to do with which of these replica layers is activated. So I'll stop here, and thanks a lot.